Hi, I'm Sylvie Thiébaux from the Australian National University, and I'm going to talk about deep learning for generalized planning. This is joint work with my colleagues, Florian Geiser, Philippe Trevisan, and Xin Xie, and with two outstanding undergraduate students we had the pleasure to supervise within the last few years at INU, namely William Shen and Sam Toyer. So they've now graduated. Sam is doing his PhD at UC Berkeley, and William is about to start his PhD at MIT as soon as COVID allows. And so much of what I'm going to talk about originated in their undergraduate thesis. So the motivation for our research was that we wanted to understand whether deep learning can solve planning problems. Now, we all know that deep learning is currently the approach of choice for solving perception tasks, such as those that arise in computer vision and natural language processing, but it's still unclear how helpful deep learning can be to approach reasoning tasks, in particular planning. So we wanted to find out. And as a starting point, rather than using off-the-shelf architecture typically used for computer vision, we thought it would be more interesting to come up with an architecture that's really dedicated to planning, that is capable of exploiting the structure of planning problems and the type of representation that we're using in planning. And so we wondered what this type of architecture would look like. Now, moreover, rather than learning to solve specific problems characterized by a specific set of object, initial state, and goal, we thought it would be much more exciting to learn generalized policies that are applicable to any problem in a given domain. For instance, a policy that is applicable to all block sort problems, regardless of the number of blocks. We also wanted to learn heuristics that generalize not only across the number of objects, but also across domains, very much like domain-independent heuristics do. So as you can see, the questions that we're asking are about learning, but we're asking them with our planning glasses on. So our answers to these questions are two neural net architectures. The first one is action schema networks, or ASNets, which we're using to learn generalized policies for deterministic and probabilistic planning. ASNets exploit the structure of planning problems, particularly exploit the precondition effect relationship captured in the action schemas for the domain. And it uses this to efficiently propagate information through the network. It also has specific weight sharing scheme, which enables it to represent generalized policies. And so I'll explain how this works. Experimentally, we find that ASNets is really performing very well when there is a simple trick in the domain that enables, that can be learned, from small planning instances, and that enables solving arbitrary instances. The second architecture that I'm going to talk about is Strip's hypergraph networks, or Strip's AGN, and we use it to learn heuristics that generalize across problem size and across domains. And again, Strip's AGN exploit the structure of planning problems, in that case, by propagating information over the hypergraph that represents the delete relax problem. Experimentally, we find that Strip's AGN produce quite informed heuristic without completely blowing up the plan lengths, but that its runtime is not competitive with that of specialized implementation of domain-independent heuristics. We published ASNets at AAAI 2018. We also recently published a much longer paper in J. And for Strip's IGN, it's being published here at ICAPS, and so I really encourage you to go and see William's talk, which will be as part of the probabilistic planning and learning session. So the plan of my talk is going to be straightforward. I'm first going to talk about ASNets, then about Strip's IGN, and then I will talk about related and future work. So let's start with ASNets. As I've said, our motivation was to really exploit the structure of planning problems in deep learning. And as you know, in planning, we make the distinction between the domains, which lists the predicates and action schemas, and the problem, which additionally specifies the objects that we have and the initial propositions that are true initially and in the goal. These propositions are instances of the domain predicates, and the actions are instances of the action schemas. So I know we all know this at ICAPS, but I thought I would make sure we agree on the vocabulary, because in ASNets, we're going to exploit this structure in terms of predicates, proposition, actions, action schemas, and their precondition and effects, in order to learn generalized policies that work for every problem that is an instance of a given domain. So this is what an ASNet looks like. So an ASNet represents a policy that takes as input features particular features representing the current state, and outputs a probability distribution over applicable actions in this current state. So I will talk in more details about the input features and output features later. I just want to focus for the moment on the structure of the network. So an ASNet consists of alternating layers of action and proposition modules, with the first and last layer being action modules, consisting of action modules. So each action layer has one action module per action in the problem. So it's problem specific. Each proposition layer has one proposition module per proposition in the problem. And there exist only connections between related proposition and action module in adjacent layer. So we're going to say that proposition and an action are related, or let's say that action A and proposition P are related, if and only if P appears in the precondition or effects of the action. Thanks to this relatedness relation, we're going to be able to efficiently propagate information through the network for the purpose of determining which actions should be applied in the current state. So let's have a look at what's in an action and proposition module. So let's start with an action module. This is the action module for the action drive shaky kitchen hall. And it's got 3 related proposition modules at the previous layer. So what we do in an action module is that we first concatenate the feature vectors that are produced by the related proposition module into a big vector. And then we apply a linear transformation by multiplying with a matrix of weight and adding a bias vector. And then, of course, we apply a nonlinear transformation to obtain the outputs. So importantly, the dimensions of these weights and bias vector are set so that the dimensions of all the input and output vectors are the same, equal to the dimension of the hidden representation. As you probably know, in a neural network, what we're trying to do is to learn, or if you prefer, optimize those weights and vectors so as to minimize a loss function. Now, in the proposition modules, things are a little bit more complicated. So this is a proposition module for the proposition at shaky kitchen. It has 2 action modules related at the same layer, and these share the same action schema drive. What we're going to do is to pull together the action modules that share the same schema here. So we're going to pull them by taking, I don't know, the maximum or the sum, pairwise sum of their elements. If we had other related action modules that had a different action schema, for instance, move shaky whole kitchen and move shaky kitchen all, then we would separately pull them. And at the end of the pulling phase, we have one pulled vector per related action schema. And then we fall back on the previous configuration, we concatenate them and apply the linear and nonlinear transformation. And so once again, the dimensions of the matrices can be set so that everything has the same size. Now, let's talk briefly about the input features. So the first layer action module receive inputs. They receive an input saying whether the action is applicable in the current state. So that's this Boolean M here. And for each proposition P, which is related to the action we're talking about, we are given the value of P in the current state and the value of P in the goal. For the outputs of the final action modules here, each of them outputs a single number or logit if you like. And we obtain a probability distribution over applicable action by passing these numbers through a softmax layer, actually a masked softmax layer, where the masks are these Booleans M, saying whether the action is applicable or not in the current state. And so the probabilities of the applicable actions is proportional to the exponential of these numbers. It's quite typical. All right, so at this point, you should be thinking, well, you know, that's great, but how are these policies generalizable to, you know, to arbitrary number of objects? Because after all, the size of the network completely depends on the number of proposition and action, which itself depends on the number of objects in the problem. So that for different number of objects, we have completely different looking networks. That's true. However, there's one thing that does not change as the size of the problem increases, and that's the number of predicates and action schemas. And so in order to come up with generalized policies, what we're going to do is we're going to transfer weights by sharing weights across modules within the same layers that are built from the same predicate or the same action schema. So within the same layer, any proposition module that's built from the same predicates will have the same weight, and any action module that's built from the same action schema will have the same weight matrix. So let's have a look what this gives us. So this is an example of an action module again. Well, that's the same example for drive, shaky, kitchen, hall. If we add at the same layer another drive action, let's say drive Bob from the ballroom to the toilet, then it would have the same weight matrix, the same vector. And we can do this because these two actions, because they're from the same action schema, have the same number of related proposition, and these play the same role. So the matrix can have the same sizes. For a proposition module, it's a little bit more complicated. So again, at shaky kitchen, add the same layer as another proposition with the predicate at, like at Bob ballroom, would share the same weight matrix. But for propositions, it's not true that the number of related action modules is the same as the domain increases. And so that, for instance, if we had another object or another room, like a ballroom, for instance, we would have drive shaky kitchen ballroom and drive shaky ballroom kitchen, also related to the at proposition here. And so this is exactly why we pull from action module with the same action schema, because at the end of the pooling phase, we will have exactly one pooled vector per action schema. And so again, we have the same number of inputs, and the weight matrices can be the same for any at proposition. All right, so ISNets are great, but they also have some limitation, and the most important one is the receptive field limitation. So this is analogous to what's happening in convolutional neural networks that process images. With the CNN, the receptive field of a neuron is the window of pixels which determines the output of that neuron. And so in the lower layers of the network, it's a very small window, and as you go up the layers, aggregate and propagate information, this is a much bigger window of pixels. Now, for an ASNet, we also have a notion of receptive field. And for a module, this is basically the set of input proposition that determine the module's output. So it's going to be a set of initial proposition, goal proposition, and well, applicability. And so as we propagate up towards the top layers here, this set of input proposition that influence the output grows, and it grows according to the relatedness of the proposition and action. However, because the ASNet has a fixed number of layers, we cannot reason about arbitrary long chains of proposition and action, so that an action here at module at the top layer here may not see some of the propositions that are given as input in the bottom layer, including some of the goal propositions. So if we don't know what the goal is, it's going to be difficult to achieve, well, solve the problem. So this is why we've decided to resolve this issue by giving additional inputs to the network. In particular, we're using inputs that are derived from heuristics, domain-dependent heuristics. We're using LM-cut landmarks and are telling every action in the bottom layer whether it's a member of the singleton landmark, a member of any landmark, or not a member of any landmark at all. And so an action at the top layer here, because it's related to itself at the previous layer, is going to know whether it's a member of a landmark or not, and that's going to give it enough information to determine whether it's relevant to the goal. So how do we train these networks? Well, we train ASNets using an imitation learning approach, which optimizes the weights of the network so as to mimic the actions that a teacher policy would take on a number of small planning problems. So our learning algorithm, or training algorithm, if you like, has a number of epochs, and at each epoch there are two phases: exploration and weight updates. In the exploration phase, we explore the training problems with both the learn and the teacher policy. So with the learn policy, we generate sample trajectory, which may end up in the goal, or it may end up in a dead end, or in another state if we exceed a certain depth. And then we use the teacher policy to generate all states that are reachable from the state along these trajectories, as well as the Q values corresponding to all of the applicable actions along these states. And we store the observed state and teacher Q value pairs into a memory. So that finishes the exploration phase. We use this kind of dual teacher-learner strategy because it enables us, first of all, to focus on the state that the current policy says are reachable with high probability, but also on the state that the teacher policy believes are promising. And this is a strategy that's, for instance, used in other systems that you may have heard of, for instance, the Dagger system. So in the weight update phase, we sample mini batches of pairs, state Q values from the memory. And we use them in order to learn to classify actions as being those that the teacher planner would choose. So the teacher would choose actions minimum Q value. And we incentivize the network to follow the teacher by minimizing the cross-entropy action classification loss. All right, so I'm now going to show you some experimental results. I'm going to present results over a number of domains, and for each of them, I will show you the cumulative coverage as a function of time. So the cumulative coverage is the number of problems solved, and for probabilistic planning, it's really the cumulative probability of the goal being reached, because there may be unavoidable dead ends. I will also, I will show you also the maximum number of problems. So what you will see for ISNet, which is in blue here, will be an horizontal line corresponding to the training time, and then it will solve problems very fast. And you'll see also the baseline planners, which can start solving problems as soon as the clock starts. We use only one core, so we're not doing experiments on GPUs in order to be fair with the baseline planners. For probabilistic planning experiments, we use LRTDP with HSDIP as the teacher planner. We've also experimented with training with LMCOT to obtain optimal policies. The baseline planner are LRTDP also with HSDIP and SIP with HSDIP. We've also experimented with LMCOT, but the results are much worse. And we average everything over 30 executions per problem. For deterministic planning, the teacher is A star with HSDIP. And the baseline are llama first, so very fast planner, but bad plan lengths. A star with LMCOT, so slow planner, but optimal plan lengths. And greedy best first search, and we include this just to show that the LMCOT landmarks or the LMCOT in itself is not sufficient to solve the problem. All right, so the ISNet version that I will show you, most of the time I'll only show you the baseline ISNet version, which is ISNet with heuristic inputs. And when there's a difference, I will show you ISNets without heuristic inputs and ISNet trained with admissible heuristics. So let me start with probabilistic planning problems and with triangle tire worlds. So this is a problem in which you need to reach a goal from initial states. At each step that you move, you can have a flat tire, and the locations in dark here have spare tires. So the only optimal solution that's got 100 probability of success is to take the outer edge of the triangle here, and of course the bottom edge as an abysmal probability of success. Interestingly, there is a simple strategy to solve triangle tire worlds. You simply need to move to an adjacent location from which there is 2 spare tires available in a row. And so this is the kind of simple trick that ISNet is capable of learning, and which is going to manage to learn using 3 training problems only, the largest one being this one. So these are the results. As you can see, we can train just for 15 minutes. And after that, in blue, we have a generalized policy that solves all of the problem, whereas the 2 baseline planner are really struggling. And by the way, we don't even need heuristic inputs here. So the ISNet version without heuristic inputs is just exactly the same. The second problem is Cosa Nostra Pizza, and we had already designed it to illustrate the issues with the receptive field. So in this problem, pizza delivery person must deliver pizza to a house starting from the shop and come back to the shop. But there are a number of toll booths along the way, and so the size is a number of toll booths. If you don't pay the toll on the way in, then the operator will smash your car on the way back. So the optimal policy is to make your way to the house, and the way in you pay all of the tolls, and on the way back you don't. So as you can see in blue here, the version of ASNet with heuristic inputs managed to solve the problem, whereas the version in orange here, which is without heuristic input, doesn't, because it doesn't even know in which direction it's going. And again, the baseline planners do even less than this version without heuristics. The last probabilistic learning problem I want to talk about is exploding blocks world. So in contrast to the two other, there's no simple trick in exploding blocks world. There's a complicated problem where blocks are set to detonate, and when you stack them on other objects, they explode these other objects, which is destroyed, and so you can't reach the goal anymore. So they are both unavoidable and avoidable dead ends. As you can see, even after 2 hours training, the version of ASNet in blue here, the standard one, is barely above the baseline planner. And you can get a little bit of improvement if you train from an admissible heuristics in gray here, but yeah. As you can see, neural networks, even ASNets, are not necessarily capable of performing very highly on these more complicated problems. Now, let's move quickly to deterministic planning. The first problem is blocks world. I need no introduction. As you probably know, in blocks world, there are simple strategies that you can take, such as unstacking all the blocks onto the table and then building the goal position. And again, that's exactly the type of strategies that ASNet is capable of doing. In fact, it learns a slightly better strategy. So in blue again, we have got ASNets, which has managed to learn a generalized strategy, and we have experimented also with tens of thousands of blocks world problems to show this. The non-heuristic input version of ASNet cannot solve all of the problems, and that's because if you have very long towers, the receptive field does not enable you to know whether all of the goals at the bottom of the tower are in their goal position. But we still do a lot better than Llama in terms of coverage, and in fact, the plan length is dramatically better than the Llama plan length. And A star and really best for such are already competing. In the two remaining problems, Gold Miner and Magic Blocks World, which are the from the learning competition, we do not quite manage to find generalized policy on these experiments, but this is not a problem with the representation, because with other hyperparameters, actually, we do find one. So this is just that our standard set of hyperparameters doesn't come up with one. But again, we do significantly better than the baseline deterministic planners. Right. So there are a few problems that we can't solve. Sokoban, because it's too complex. Some people who have solved Sokoban have used tens of thousands of examples. Parking, because the model is such that there's too many ground actions, so the ASNets become too big and we can't grow and we can't train them. And a puzzle, we find a policy that's generalizing just for 8 tiles, but does not generalize above that. So what are we working on, or what have we done recently with ASNets? So firstly, we've started to work about integrating generalized policy with search. And so for instance, in our SOX 2019 paper, we showed how to guide Monte Carlo tree search with generalized policy in order to improve both the ASNet policies and the search. We've done this via, of course, using the policies for rollouts, but also by biasing the UCB1 exploration term to select actions that ASNet thinks are promising. I think there's a lot more to do in terms of integrating search with generalized policy, and I will briefly talk about it at the end in the future work. We've also started to work on visualizing and interpreting ASNets. As you know, neural networks are notoriously difficult to understand and explain and analyze. But in the case of ASNets, this is somewhat mitigated by the fact that the ontology of the elements of the network, like proposition and action, maps the ontology of the tasks. So what we have experimented with is generating sparse networks by using appropriate regularization term in our objective, and translating those networks into a set of equations, which are such that someone like me, a computer scientist, would be able to convince myself that this is indeed a generalized policy. But what would be interesting for the future is to do some reasoning over these equations, to analyze the network, prove properties of the policy, and explain the policies. So for the second part of this talk, I'm going to talk about STRIPS hypergraph networks, or STRIPS AGN. The motivation behind STRIPS AGN was to learn generalized heuristics, or domain-independent heuristics, if you prefer. So the people in these workshops are really well placed to know that over the past 2 decades, the planning community has come up with many new domain-independent heuristics, which have been instrumental in pushing the field forward. And so what we wanted to do was to see whether we could learn these heuristics entirely from scratch by training on optimal plans for a set of STRIPS planning problems. When I say entirely from scratch, that means that we're not learning to improve existing heuristics, we're not learning a portfolio of heuristics, and we're not using domain-dependent uncrafted features to learn them. We're only using the plans and basic domain-independent features. And so we wanted to learn heuristics generalized to problems from different initial state, different goals, different number of objects, but also problems from different domains, including different domains than those we trained on. And so I think this latter point, generalizing across domains hasn't really been done before in planning. So that's part of what makes our approach unique. So as with ASNets, we wanted to exploit the structure of planning problems, or rather planning heuristics here. And so we decided to focus on delete relaxation heuristics, which, as you know, ignore the negative effects of actions. The delete relax problem P plus for a problem P is the same as problem P without the negative effects, and that can be represented by a hypergraph whose vertices represent the propositions in the problem, and whose hyperedges represent the action that links the preconditions, or the centers of the hyperedge, to the positive effects of the action, which are the receiver of the hyperedge. And so what we wanted to do was to exploit this hypergraph structure to learn distant function over the hypergraph that reflects the cost to reach the goal in our training set. Now, of course, that's only an hyperedge. I'm letting you imagine what the hypergraph looks like. So more precisely, what we want you to do is to learn a heuristic function H that takes as inputs the hypergraph representation of the delete relax problem and outputs a heuristic value. Of course, the hypergraph is decorated with input features, and we use only domain-dependent basic features. So for the vertices, we encode whether the proposition they represent is true or false in the current state and the goal. And for the hyperedges, we encode the cost, number of precondition, and add effects of the corresponding action. We could have a much richer set of input features, but yeah, we didn't do that. It would be interesting, for instance, to experiment by adding the number of delete effects. So how do we learn these heuristic functions? Well, we use hypergraph networks, which are our own extension of graph networks by Battaglia et al. So graph networks are a generalization of existing learning models, including deep learning models, and hypergraph networks are a slight generalization to multiple senders and receivers. The basic building block of hypergraph networks is the hypergraph network block, or HGN block. And an HGN block transforms an hypergraph into another using a number of functions that update the features of the hypergraph and aggregate pull features and pass information through the network, through the hypergraph, using essentially message passing. So in our case, a hypergraph is represented by a number of hyperedge features, vertex features, and global features, where the global features are going to encode the heuristic function. And so we're going to need 3 update functions, which are represented in green here, one for the hyperedges, one for the vertices, and one for the globals. We're also going to need 3 aggregation functions represented in red, which are going to pull various features and aggregate information through the hypergraph. So in one round of message passing through this hypergraph network block, we're going to perform the following computation. Oh, before that, I should have said that, very importantly, these update functions are learnable, so they're going to have parameters which we're going to learn, and in our case, we'll represent them by linear perceptrons, and so we're learning the parameters of this perceptron. So I was talking about the various computation steps as part of one round of message passing through an HGN block. And so this is going to go as follows. Firstly, we're going to update all the hyperedges features. So for each hyperedge, where the update function is going to take as input the current features of the hyperedge, the features of the vertex, which are the receiver and sender of the hyperedge, and the global features. And it's going to produce a new set of hyperedge features. Then we update all of the vertices. So for each vertex, we're going to take as input the aggregate information of the hyperedges for which this vertex is a receiver, the current vertex feature, and the global features. And then finally, we are going to update the global features from the aggregate information of the vertices features and the hyperedges features. So that's what's happening in one round of message passing through the hypergraph. Now, in order to learn heuristics for strips, architecture in strips HGN uses 3 of these HGN blocks within what's called a recurrent encode process decode architecture. So we've got an encoder block, a decoder block, and a core processing block, which is going to be applied m times. So it works as follows. Firstly, we pass the input feature and the hypergraph structure to the encoder block. This encoder block is simply going to have 2 encoding functions applied separately to the vertices and the hyperedges, and that's going to give us initial latent proposition and action features. Recall that, as I've said, we are using multilayer perceptron to encode all of the update functions. Now, these latent features that we obtain are going to be concatenated with the recurrent features obtained at the previous round of message passing and pass on to the HGN core block. Now, initially, we don't have recurrent features, so we're simply going to concatenate the latent features with themselves. So that gets passed to the core message passing block, which does pretty much what I've shown you before, except that it does this on the concatenation of the latent features and the recurrent features at the previous time step. And so at the end of that, what you get is a latent heuristic value and updated proposition action features. And we're going to do this. Again, we're going to repeat this operation, again, concatenating the results with the initial latent features and passing on messages through this core block. And we're going to do this m times. So we're going to have m message passing round, at the end of which we will have a final updated latent feature, which we're going to decode to produce a heuristic value. So the decoder is very simple, and it's one linear perceptron. All right, so how do we train those networks? Well, we generate examples by first generating optimal plans for a set of planning problems, and then the training samples are the pairs, hypergraph, optimal distance to goal from each state encountered in the plan. This may not be the best strategy, but so we have one sample per state in the plan. We're optimizing the weights by casting the problem as a regression problem. We're trying to predict the optimal heuristic value here. And we do this by optimizing the mean square error loss, so the difference between our prediction and the correct value square. And we are actually considering, when we're doing this, all the various intermediate heuristics values that we're obtaining at each message passing round to accelerate convergence. Now, as you can see then, we're really trying to learn H star. I mean, it could be argued that we should learn H plus instead, because after all, this is the optimal delete relax heuristic, but we're aiming at learning H star because we believe that the network is capable of representing it, at least if you fix the domain. In any case, whether we use H star or H plus, we're not going to have any admissibility guarantees for this heuristic, and so that's one of the weaknesses of the approach. So I'm going to show you some experimental results. As for ASNets, we're only using one core, so we're not using GPUs. We're training on A star as implemented in fast downwards, equipped with ZLM cut heuristics. This is how we get our optimal plans. We're going to train for each experiment 10 networks, giving them 10 minutes training each, and we're going to use number of message passing 5 and 10. The evaluation is also on A star and fast downwards. We're using 5 minutes per problem per heuristic, and for each of these heuristic, we record the number of expanded node, the runtime, and the cost deviation from the optimal. So the cost of the plan produced minus the cost of the optimal. And we're going to compare Strix AGN heuristic for the network that gives us the best overall coverage for the experiment, which is often obtained for m equals 5, because the accuracy that you're getting with m equals 10 is not enough for to compensate for the fact that the runtime is basically doubled. And we're going to compare Strix AGN with baseline heuristics, LMCut, and HFF. Now, I should warn that now it's very difficult to compare non-admissible heuristics, especially with the star. So this is not meant to be you know, a comparison like, well, my heuristic's better than yours. It's more supposed to be an illustration of the fact that this idea of hypergraph networks is promising, and these heuristics have their place within the scope of domain-dependent heuristics. So I'm going to show you two types of experiments, one which we call single domain experiments. And in these experiments, basically learn on small problems from a given domain, and we're going to evaluate on larger problems from the same domain, with the domains being Gripper, Bloxwald, Ferry, and Sokoban. And in the second type of experiments, which are the multi-domain experiments, we're going to learn a single heuristics from small problems from several domains. So Gripper, Bloxwald, Zeno in this instance. And then we're going to evaluate on larger problems from domains, both from domains from which we have learned, but also from domains from which we haven't learned, like in our case, Ferry and Sokoban. So I'm going to present the results domain by domain, starting with Bloxwald. So in the top here, you have the single domain experiment for Bloxwald, and the bottom, you have the multi-domain experiments. Left-hand side, number of expanded node, middle runtime, on the right, the cost deviation. Strix AGN is in blue, in green we have LMCut, and in orange we have FF. So I want you to observe a number of things. Well, firstly, the runtime of Strix AGN is not competitive, at least for the small problems. On the other hand, it needs to start getting competitive for larger problems, and the runtime does not nearly increase at the rate that the other heuristics increase. For Bloxwald, we expand much fewer nodes, so several order of magnitude fewer nodes than the other heuristics. Well, I'm guessing that the price to pay for this is that we're using a star. This means the plan's not always going to be optimal, unlike, let's say, FF, which always return the optimal plan for Bloxwald. When we're using the domain-independent heuristics, the coverage is less, as you can see. The runtime is just as bad. The number of expanded node is starting to be quite similar to that of the other heuristics, but on the other hand, the plan length for the problems we can solve is optimal. But for Gripper, well, this is quite successful. We have a large coverage in comparison to the other approaches. The runtime is good, except for the very small problems. And the cost deviation, well, the plans are not optimal. I think Malte Helmut tried to explain to me once why, if you have a heuristic, even, you know, deviates from one from the perfect heuristic function, you could get this kind of behavior. All right, and when we move to the domain-independent setting, then the results are worse, still better in terms of coverage than the other heuristics. And actually, on the other hand, the plan length is better. Theory is another problem in which we're quite successful. So as you can see, the number of expanded nodes is quite a bit less than that of the other heuristics. Runtime is pretty good, and even the plan length is pretty good. And what's more surprising is that that remains the same for the domain-independent heuristics. There's hardly any difference. It's not the same, on the other hand, for Sokoban. There's a big difference between the single domain and multi-domain experiments. And generally, the results aren't fantastic. We don't have the same coverage as the other two heuristics. Runtime is bad. On the other hand, plan length is pretty good with respect to FF. Quasi optimal here and completely optimal there, which for Sokoban I think is pretty good. So what are we working on currently or about to work on? Well, obviously the runtime improvement is a big priority. So there are a number of approaches that you could use to achieve this. You could use GPU and parallelization. You could optimize the implementation. And you could even do simpler things like using richer features, or even a different type of graphs. After all, you know, there are many graphs that have been used in planning. There's no reason why we should use this one. We could also have a look at the design choices that we made in the same line as what Patrick Faber did at AAAI 2020 for a simpler setting where they use linear perceptron and only generalize across initial states. And so I think we could get quite a bit of improvement like this. Another thing that we want to work on is different settings. So with hypergraph networks, we could be learning policies with slightly different architecture. We could be working on satisfying planning and learning to rank. And we also want to look at richer representation, for instance, probabilistic planning. So to finish, let me talk about related and future work. So firstly, let me say that learning for planning has existed for a long time. It's probably as old as learning and planning themselves. And there are a number of good surveys. In particular, I would recommend the paper by Sergio Jimenez and colleagues, which gave a very comprehensive survey in the Knowledge Engineering Review. That was, however, pre the deep learning era. I would also recommend the related work section of our ASNet paper, which is much more focused than the survey I mentioned, but which is covering the two main topics I'm going to talk about now. The first topic I want to talk about is deep learning for planning. So what's the related work there? Well, the first work I think I've been aware of in this area was the work of my colleagues, former colleagues, Olivier Buffet and Doug Aberdeen. So you may have heard of the factored policy gradient planner. It was basically applying deep reinforcement learning to solving individual planning problems. And this was quite successful. The planner won the 2006 probabilistic planning competition. Now, in the post-deep learning era, there's been quite a number of interesting works on learning PDDL description, for instance, PDDL description for images, using neural networks by Adasoro Azai, and also learning neural network models of transition functions, typical of what you have in planning. And so you can then solve the planning problem using MIP, whereas before you would solve it with these approaches with the classical planner. There's been also recently interesting work on learning planning portfolios with convolutional neural nets and graph neural nets by Simon Sievers and people from Freiburg. And if we look now at learning generalized policies, initially there was some work by Edward Gorshev on using convolutional neural networks from images, for instance, to learn a generalized policy for Sokoban. However, that used a large number of training examples and uncrafted features. And so this is why, in contrast, what we wanted to do was to have an architecture dedicated to planning, which enable us not to have these uncrafted features and which enable to use only a small number of training examples. Now, in parallel, there was work on doing very much the same with RDDL, for instance, by Alan Funn's group, although they didn't learn generalized policy, but perhaps more importantly by Mozam's group. So with two systems, TrapsNet and SimNet. SimNet is quite interesting because it doesn't require grounding, so it uses graph attention network, and yeah, it doesn't have the same issue as ASNet, for instance. When it comes to learning generalized heuristics, using deep learning, there's been less work, but as I've mentioned, there's this work by Faber et al. On quite careful study of the hyperparameter space for linear perceptron. The second type of work I want to mention is work about representing, synthesizing, and learning generalized policies and heuristic, not necessarily with deep learning or with any form of learning. So the first type of work I've been aware of, well, I think when I started, you know, my master's or something, was by Zohar Mana and Richard Waldinger. They had this paper called How to Clear a Block, where they use automatic deduction to to synthesize recursive programs that could do that. There's been a lot of work in the early 2000s on learning decision lists by Ronnie Cardon, Sang-Wook Yoon, Alan Fern, etc. and in particular by Marion Martin and Hector Geffner, who suggested the use of concept languages to have a really rich language represent features that would be interesting to embody in decision lists. Then this was followed by a lot of work on first order and relational MDPs, which in planning was initiated by Frank Boutillier. There's also lots of work on learning search control knowledge, for instance, by Anne Fern and later by Thomas de la Rosa. But recently, there's been a new wave of work, which in my mind, and I could be wrong, I associate with Sridhar Srivasta's thesis at the beginning, and then with people like Hector Geffner, Bly Bonnet, all these groups, and Javier Segovia, and so on. And so this work is about abstractions that enable synthesizing generalized policies, and about characterizing their properties, for instance, whether they are sound or complete, looking at how to represent them with languages, for instance, with this qualitative numeric planning language, how to synthesize the generalized policy from these abstractions, for instance, using non-deterministic planning, how to learn this abstraction, and so on. And for a really great talk about all this line of work, I suggest you look at Bly Bonnet's invited talk. I should say that I'm also looking forward to the ICAPS Bridging the Gap between Reinforcement Learning and Planning workshop very soon. All right, so what do I want to work on? What do we want to work on in terms of future work? Well, firstly, I think we should really try to get some cross-fertilization happening between the deep learning and reasoning approaches that I've mentioned. Deep learning looks like it's more flexible. You can easily do a lot of things. It seems more effective experimentally, but on the other hand, the reasoning approach is beautiful, it's much more principled, it's more interpretable. And so I think that this cross-fertilization would enable to really study more carefully the power of various representation and compare this representation. For deep learning, it would enable proving properties of the representation and making them more interpretable. I'm also interested in removing some of the limitations of the current architectures, in particular grounding and things like ISNets, and looking at richer form of planning, spatial observability, time, numeric planning, etc. And finally, I think there's really a lot to do in terms of much more closely integrating generalized policies learning with search. So first of all, there's many ways of guiding search with generalized policy, and it's not just with Monte Carlo tree search or even with systematic backtracking search. You could imagine doing that with large neighborhood search, for instance. And the nice thing about generalized policies is that you can continually improve them and learn as the search proceeds, because you don't even need to reach the goal to have examples from which you can learn a generalized policy. You can also use leapfrogging. So you can use your current generalized policy to guide the search for generating bigger examples for bigger problems that are then going to be used to improve your generalized heuristic and so on. So I'm quite excited about these topics, and I hope to see a lot of work in the near future in that. All right. Well, thank you very much for listening.